So I wanted to take a couple of minutes and highlight a few slides that we didn't have a chance to get to in lecture that are going to become important for your take-home portion of your exam that have to do with sort of non-traditional carbohydrates. And we're really sort of thinking here about either artificial or non-caloric natural sweeteners. And so I have about 4 or 5 slides here to kind of highlight. They have notes on them from previous class that we took notes, but I'm just going to kind of highlight some important pieces here. I know they're going to look busy, but again, I'll walk you through what we have here. So big picture thing here, when we're talking about something that's not sugar, but is serving sort of as a sugar substitute, there's a couple of things that are really important here. The first is that this molecule somehow has a structure that allows us to signal our sweet taste receptors in our mouth. And so that's why it's able to be a sugar substitute, is our bodies taste it as sweet. And so here we can see sort of in this table here, we can see the relative sweetness of some sugar alcohols. We'll talk about what those are in just a second here, but we can see that this is relative to table sugar. And so we can see that a value of 1 means it basically has the same sweetness as table sugar. So again, table sugar being sucrose here. So another thing to highlight, and this is going to become important as we talk about many things that are sort of substitutes in our food world, is talking about why something might be either low calorie or no calorie. Kind of a third thing that I don't even have listed here, maybe I'd call this a 0, is maybe it's not even ingested into your body, so it stays within your gastrointestinal tract. So obviously if you can't get it out of your intestinal tract, we call that something like a fiber. It's not anything that you bring in for a fuel. So that's kind of a 0 point here. But for things that you do actually bring into your bloodstream, if it's not metabolizable, then it's non-caloric. Or if the concentration of it that you need to have is so low that essentially it equates to something negligible, then we can basically say it's no calorie as well. So we'll talk about this as well when we talk about fat substitutes in our next learning unit here. So when we're talking about sugar alcohols, basically they are taking what was a carbonyl-containing functional group in an aldehyde in these aldose sugars, doing some chemistry with them and converting them into sugar alcohols. And so again, it's reduction of this aldehyde group to an alcohol. Now, this can happen kind of synthetically, but these are often things that are found naturally as well. So I'm going to highlight a 4-carbon, 5-carbon, and then 6-carbon sugar alcohol. And so again, sorbitol is going to be the sugar alcohol that's derived from glucose. So this is something that's actually found naturally. Xylitol, this is actually a favorite sweetener of mine, is a 5-carbon sort of version of this. And then erythritol is found here. So again, kind of highlighting some important components of this is we're going to call it a sugar substitute. Not only does it have to taste sweet, but we do need to think about how many calories it's worth. And most of these tend to be at least half, if not fewer than half, of the calories of sucrose. So that's important. So they're not as high in calories. And some of them, like erythritol, are actually quite low in calories as a comparison. And part of this reason, though, is because it has minimal absorption in their small intestine. Even if it's not absorbed, it's not really metabolized. Most of it is actually excreted. And so this GI stands for the glycemic index. So it's sort of impact on the ability to raise blood sugar levels and thus have an insulin response. So again, 60 here is sort of our base level for table sugar. So we can see that these have a very small glycemic impact. So again, minimal response to our insulin levels. And that's really important when we want to consider that hormonal component. The last thing, I'll just kind of comment here, I'm not going to say too much about it. Some of these sugar alcohols are found in a lot of chewing gums, and that's interesting because your oral microbiome, bacteria that live there, cannot use sugar alcohols for fuel, and so this actually helps prevent their growth, and so it prevents tooth decay in that regard. And an interesting kind of component here, E. coli 0157H7, this is the bad E. coli. When you hear about sort of tainted meat and meat outbreaks, it's usually this very problematic strain of E. coli. And so these will actually grow on sugar alcohols. So this is actually a test for bad E. coli, is seeing if your bacteria will grow on these sugar alcohols. If they do, it's an indication that it's this bad sort of sugar. I do want to sort of talk about something called inulin and resistant starch. So these are interesting molecules in that this is unusual. It is found naturally, but it's unusual in that we have a polymer of fructose that we're going to have here. Normally all the polymers that we've talked about are polymers of glucose. So this is an unusual fructose polymer. This is how plants actually kind of have an energy reserve. And it has a very interesting linkage. Again, one of these head-to-head linkages. It's a beta 2,1 linkage that we see, sort of a head-to-head linkage in fructose here. And because we've got this beta linkage, it's not digestible by us. So basically, these go through our small intestine fairly unchanged. And so this is what we refer to as soluble fiber. It's not the bulk fiber like we have with cellulose. So this is sort of a soluble fiber. And we call this resistant starch. So resistant starch basically is something that is not able to be changed in our intestinal tract. So again, we should highlight that inulin is this structure here. This is unable to be digested because of this unusual beta 2,1 linkage in the fructose polymer. Resistant starch is actually alpha amylose, so this is a glucose polymer. And resistant starch also goes through the small intestine unchanged. It has to do with kind of the structure of it. It's allowed to sort of pass through and get to the large intestine largely undigested. And so once it's in the large intestine, then your bacteria can ferment it. And we can create these small chain fatty acids that we talked about in our learning unit on fatty acids. And again, these are going to be really important. Butyrate is an important one that allows for colonocyte fuel. And again, good bacteria actually can consume butyrate for fuel. So butyrate is one of these really important small chain fatty acids that we see. So just one thing to highlight that's important in terms of the sources that we see for resistant starch. Bananas, specifically not ripe bananas, so green bananas are a good source of this resistant starch. And even things like rice and potatoes are a really good source of resistant starch, but if they're cold. This temperature thing is really important because it's this coldness that sort of pulls this together and makes it sort of indigestible. I don't know if you've ever sort of had rice that got cold and kind of if you're trying to clean out the bowl afterwards, it's really hard to clean. And that's partly because we've got that resistant starch that sort of has a different structure that's a little bit impermeable to digestion by us in our small intestine. So I've intentionally color-coded this next slide yellow and pink and blue because this refers to the color of the packets that you're going to see on your restaurant table that contains these artificial sweeteners. So the previous two slides kind of highlighted things that are sugar substitutes that are found naturally. Again, some artificial sweeteners here in Splenda, which is also called sucralose. Aspartame, trade name is NutraSweet, and then saccharin. I think this is equal on the blue packets on your table. I kind of wanted to just highlight some things structurally that we have here. A lot of times you'll hear people talking about, well, sucralose is just like sugar because it's made from sugar. Okay, the chemical modification is to convert 3 hydroxyl groups into chlorine groups. It's done synthetically. This is nothing that happens naturally. So yes, it's made from sugar, but that does not in any way make it, like sugar. So again, has a chemical structure that signals our taste receptors that it is sweet. So just some interesting backstory on this. So again, while researching ways to use sucrose for industrial use, a researcher was told to test a chlorinated sugar compound. He thought that they asked him to taste it, or that's what it meant to test it. So he did, and he found it to be exceptionally sweet. It is 600 times sweeter than sugar. Why it is non-caloric is it's not metabolized. It's actually not even really absorbed from your intestinal tract, which is why some people consider it to be safe for humans because it doesn't even get into your bloodstream. It's very heat stable, so you can bake with it. But again, some of these things are problematic because we question their effect on our microbiome. Maybe this is something that's not good for you because even though you don't get it into your out of your digestive tract, it stays in there and subjects your microbiome to these foreign chemicals. Talking about NutraSweet here. Generic name is aspartame, trade name is NutraSweet. This is really a little synthetic peptide. So interesting story. Again, it was synthesized as an intermediate in making an anti-ulcer drug, and the researcher discovered its sweet taste when he licked his finger, which had become contaminated with it. And he went to, again, lift up a piece of paper, had gotten contaminated with it, and just licked his finger. So just some crazy sort of things here where we see chemists not having kind of proper protocol. Another one of these that's significantly more sweet than sugar. This is something that's metabolized. It's metabolized like a little peptide, 4 calories per gram, but because we need so little of it to have that same sweetness, it really is not considered to be anything that we can consider caloric. This is not heat stable, and in our learning unit next year, next semester, when we talk about protein metabolism, we'll talk about the disease phenylketonuria, which is something where people have the inability to metabolize phenylalanine. So again, here we can see that this is phenylalanine as an amino acid. So again, we've got aspartic acid, and then we've got phenylalanine here that we hook together, and we make the methyl ester of that. So we'll talk a little bit more about that one later. Saccharin here, this is probably one of the oldest artificial sweeteners. There's a chemist working on coal tar derivatives, and again, noticed a sweet taste on his hand one evening and connected this with the compound that he had been working with earlier in that day, which is a benzoic sulfamide. Horrible. All 3 of these situations came from chemists doing some suspect things in the lab with just licking their fingers. But another substance that's significantly more sweet than sugar. This substance is not metabolized, also heat stable, but it's really not something that a lot of people choose to consume because it's potentially carcinogenic in humans. And so saccharin is something, and some people find it to have a pretty bitter taste. So those receptors on their tongue for bitter also sort of trigger in addition to sweet. So these again are artificial sweeteners. Personally, I would avoid all 3 of these. I would not consider consuming anything. There's a lot of data out there that actually indicates that there's significant effect on your microbiome, that they potentially make you crave sweets more. And that they actually have a negative impact for people who are using those as a way to lose weight. They actually find that these individuals oftentimes gain more weight. So I would avoid any of these artificial sweeteners. So the last thing to kind of talk about here is, well, okay, what can I use? You know, those sugar alcohols are an option. You know, talking about inulin and resistant starch, that's not really a sugar substitute. So I wanted to talk about a couple of alternative sweeteners, highlight again why they are sweet, and then you know, indicate that it might be something you might want to consider trying. The first one is called monk fruit. These are naturally derived sweeteners. So again, monk fruit is this subtropical melon cultivated in remote mountains of southern China for centuries. So again, there's a lot of history with this. It's very rich in what we call glycosides, which is basically sugars on another substance. So we can see here that we've got a steroid backbone, that we basically use that hydroxyl group on a steroid backbone, and we're going to kind of decorate with sugars. And so we've decorated with a bunch of these sugars that we have here. We've got sugars that are sort of sticking out here, and those are what we can use to signal sweet on the taste buds. So 300 times more sweet than sugar. But importantly, these are not metabolized. They're not absorbed in the small intestine, probably because we have the inability to break these linkages, freeing these sugars to be kind of taken in the small intestine. These, however, can be degraded by your microbiome in your large intestine, and this aglycone core, this sterol core, can be absorbed, and that can be metabolized and excreted. So you may have some steroid sort of backbone that gets in to your bloodstream in your large intestine, but again, this is not something that contributes to, you know, a change in your glycemic index or your insulin levels. So in that way, it's considered to be a really good alternative sweetener. Stevia is maybe something that you've heard about, maybe a little bit more than monk fruit, but a very similar type of a situation here. We're going to have a steroid-like backbone, and we're going to decorate it with sugars on here. And again, these sugars that are hanging off here are what allow us to signal those sweet receptors in our mouth. So again, stevia is a sweetener and a sugar substitute that we extract from the leaves of the stevia plant, which is native to Brazil and Paraguay. So again, very rich in these glycosides, not as sweet as monk fruit, but 30 to 150 times sweeter than sugar. But again, similar biochemistry, not metabolized, so it's not absorbed in the small intestine. Your microbiome is going to finish sort of this degradation process, does have the ability to break down these linkages, and leaving this steroid core that is absorbed, metabolized, and then excreted. So some alternative sweeteners that you might want to consider are stevia and monk fruit.